Bluetooth. Get it straight.
So let's look at Chapter 8 again. We covered most of Chapter 8 in the first part of the lecture on Tuesday. Today we want to tie up some loose ends, looking at the head loss, mainly these minor head loss contributions here, which they have to do with the with elbows and joints and valves, etc. on a pipe network or pipe system. These have head loss contributions as well, so we got to figure out how to handle those, but they're pretty easy. And then lastly, some multiple pipe systems and pipe networks. So this is when pipes split off into parallel or go in a loop or in a network, as in a pipe distribution in a town. So head loss, remember we used the Moody diagram to figure out the friction factor. This can also be gotten using what's known as the Colebrook formula. But notice in this formula we have the friction coefficient here and here. So it's not an explicit formula, so you still have to iterate. So it's up to you sometimes whether it's easier to use Colebrook or to use the diagram. But if you had Colebrook programmed into your calculator or to a root solver in MATLAB or Excel, you could use it quite easily. So why do we care about head loss in pipes? Well, I think you already know that. We have to determine the energy in order to know how much pumping we're going to need to do. And we'll learn about pumping more in Chapter 12. So we have this head loss with energy in it. We've seen that before. And this head loss now, we used to be sort of given that head loss, or we'd figure out what the head loss was from the problem. But now we're going to figure it out just explicitly from the velocity mainly and the pipe characteristics. So here's the major head loss, we call it. It's kind of a strange name, but the major head loss has to do with just the head loss having to do with the pipe, and if the pipe is fairly long, then it will be the major contributor of head loss. If it's fairly short, it will not be the biggest one, but we'll still call it the major because we call the pipe part the major. So that's pretty easy. It scales with the V squared. These energy terms like head loss scale with V squared. So dependent on the length of the pipe, the diameter of the pipe, and this friction factor that we get from Moody or from the Colebrook equation. But as we mentioned in the outset here, there's other factors other than pipes. There's valves, pressure reducers, splitters, etc., etc. So there'd be other aspects of head loss. Now we still, we call these ones minor head losses. So they have to do with all the parts and accessories and fittings. They also scale with the velocity squared, and they have a constant factor called the loss coefficient. And this is something that sort of comes on the box when you buy a valve or buy a fitting. And these are empirically determined by putting these things in pipe networks and putting flow through them and seeing how much pressure drop you get across the system. So the textbook has these tables. So these are, consider these as rough estimates for KL because all the results are going to be a little bit different for the specific manufacturer's parts. But this is enough to a good set of pipes. We have some elbows, some 180s, some T's, some unions, and some valves. That's a pretty good cross-section of things to play with while we're just doing some problems. So an alternative approach for computing minor head losses is to transform them into equivalent lengths of pipe. But in all honesty, most of the time you see this approach where you just do the KL. You put that in as the head loss. But if you want, you can turn it into an equivalent term like so, where this is not a real length, it's just the right length to give you the same value as over here. So mainly we look up the KLs and we use these, and we don't do this one too much. Non-circular conduits, so we get square concrete pipes or square rectangular ductwork, these sorts of things. So for laminar circular pipes, we get a friction factor that's inversely proportional to the Reynolds number. Non-circular ones, it's a similar relationship, but it's not quite 64, and it really depends on the conduit type. So there's a C is a function of conduit type. You can see that in table 8.3, and the length scale used for R is different too. This is an interesting parameter called the hydraulic diameter. So it's kind of the right characteristics of the geometry of where the fluid is hitting the wall. and it's equal to 4 times the area divided by the wetted perimeter. So this is conduit perimeter that's in contact with the fluid. So when it's full, it would just be the whole conduit perimeter. If it was not quite full, then it would be just the part that's full. We'll see that in open channel hydraulics, where this hydraulic radius or hydraulic diameter is an important parameter. We're not going to do too much with this, but just to show you how this works. And now we get into some multiple pipe systems here. The multiple pipe systems might be a serial system where we just go from one diameter here down to a smaller diameter, reducing to a still smaller diameter. Or they may be parallel system where we have these tanks are connected and the water can go through all these directions. So if you stared at these things for a while, you would probably come to the conclusion that continuity or flow in equals flow out means that the flow has to be the same in this serial case all the way down the line. It couldn't be a fast flow here, it couldn't be a bigger flow here and a smaller flow here. If it's all moving through there in a steady system, then the flows have to be the same. The velocities would be different, as you can see by the diameters, but the flows would have to be the same. And this head loss would be equal to the sum of the head losses in each of the segments. So you could just use each segment with that major head loss term that we had before that scales with v squared and figure out the individual head losses and add them together. Now in parallel, it's a little bit different. You have to think of the continuity as well. So the flows going through, so you get 3 flows going through the pipe and they have to equal the total flow. Obviously that's kind of a continuity sort of thing. And then the head loss is kind of the key here, is that the head loss in parallel is going to equal any one of the head losses. So in other words, the flow is going to take the path of least resistance. So the energy is going to distribute itself such that the head loss is the same in all of the pipes. Because if it found a better way, it would take the better way. So it's equilibrating it until it comes to a point where all the head losses are the same. In loop systems where we have nodes, like here, where we've got the pipe coming and all of a sudden branching off into 2 pipes, we have to remember that the sum of the flow at the node is equal to 0. So flow in has to equal flow out at the nodes. And between that and the arguments we just made about flow in parallel and stuff, we can usually figure out how these systems work. And I think I have one on the homework where you were looking at some reservoirs and they branch off and it's not quite clear which way they're going. So take a look at example 814. Try to write it here, my terrible pen handwriting. So if you look at example 814 for reservoirs, you'll get some help on that homework problem, which will be a little tricky. So for pipe loop systems, it involves both serial and parallel systems. So you get the nodes. So there's lots of nodes here. Here's a node right here. Here's another node right here. So at those nodes, remember the flow in is equal to the flow out. And there's also these loops. So we've got these loops going on. And loops are important too. You can look at the head loss across those loops. And it turns out that for a loop, starting at one location and returning to that location, the net head loss has to be 0 around a loop. So this is for a loop. Should spell that out pretty clearly, not for the whole system, obviously, or that would be strange. Probably wouldn't need much pumping and stuff, but for each loop, the head loss around that loop has to be equal to 0, just like we said before. So that's it for Chapter 8, and the main things in Chapter 8 are these major and minor head loss contributions that scale with v squared, and you get the minor ones which have the KL value involved, and the major ones which have this friction factor involved. And so these are the two ways that we sum up the head loss in our pipe network. It gets a little more tricky if we have the pipe network. So these ones, I should say, these basic ones, F and KL, are for individual pipes, and they're moving along through their fittings. And then if we get the loops and networks, we add that one more layer of complexity, so we can do some simple ones there in the homework. Good luck with that homework, and we'll see you next week.